Thank you, and welcome to HAO Colloquium, the first term this year. And our today's speaker is Dr. Stan Solomon. Really, no need for introduction, so I just connect a few dots. The dots are Harvard, Michigan, HAO, CU, HAO. And he was involved in some major missions. He was an interdisciplinary scientist for NASA timed mission, and then the deputy PI for Snowy. And now he's heavily involved in gold, especially on the forward modeling, and he's going to tell us more about that today.
Thanks, Huntley. That was a perfect introduction. I asked him to keep it simple. This is really just a fill-in seminar. A month ago, Huntley mentioned that the early January slot was open. He didn't know how he was going to fill it. I said, well, I'll talk. And I would just like to take the opportunity to give a sense of things I've been working on in the last few months and get a little discussion going for anybody that's curious about this mission or what I've been doing for these simulations or why I'm doing them, and ask questions. So I'm going to try to keep the lights on, make sure everybody stays engaged. If you can't see the images, Hanli will kill the lights. So I'm just going to give an overview of this mission. It's called the Global Scale Observations of the Limb and Disk, or GOLD. Give a brief description of the instrument, the measurement technique. Then I'm going to talk about what I've been doing, these modeling and Airglow simulations, which I think are very important for this type of remote sensing observation, and a little work in progress stuff I've been doing over the holidays on radiative transfer. The idea of global imaging of the Earth, of course, dates back to the Apollo program. Many of you may recall the famous whole Earth picture. Well, they also took a whole Earth picture in the ultraviolet. This is 1969, I think. John Young, astronaut John Young, with the Apollo 16 far ultraviolet camera, which was built by George Carruthers out of Naval Research Lab. No, 69 would have been the 72, because this was Apollo 16 was one of the last missions, and it was 72, sure, and just before this was not the famous 6 iron that Alan Shepard hit on the moon. I think that would have been Apollo 17. So this was close to the end. But this is the kind of thing we would have gotten all the time if the Apollo program had continued. And it's iconic image because it's a very old type of technology, actually intensified imager with film. But it's taking images in the far ultraviolet, the region from about 1,000 angstroms to 2,000 angstroms, just longward of Lyman alpha, and even in this very low resolution image from far away, you can see the basic features of the far ultraviolet airglow, which are diagnostic of particular processes in the Earth's upper atmosphere. The illuminated disk here, this is the day glow caused by sunlight impacting the upper atmosphere, causing photoelectrons and exciting the O2, the N2, the molecular nitrogen and oxygen emissions. This is the aurora in the southern hemisphere. From the tilt of the Earth, you can see the southern hemisphere in this, and these are this is the ionosphere. This is the equatorial ionization anomaly that's very prominent at night. Of course, the ionosphere is also glowing during the day, but it's drowned out by the day glow. Yeah, Mark. This day glow is a type of fluorescence. I'll briefly touch on that later. I'm not going to go into the emission generation physics too deeply, but I discuss it. This is supposed to be discussive. If people want me to describe this, I'll go into it a little more. I don't have good slides on it. Basically, the sunlight, extreme ultraviolet sunlight hits the atmosphere, ionizes something. The ionization creates a photoelectron, which has additional energy because of the additional energy from the ionization event. That photoelectron hits something else, say an atomic oxygen atom, and excites it. And then that atom emits in the far ultraviolet, or somewhere else, but in this case, far ultraviolet. Now, there's also a lot of actual fluorescence here. Solar sunlight at 1304 angstroms hitting atomic oxygen and just fluorescing because that's an allowed transition. But the transitions the emissions I'm going to talk about today are primarily photoelectron impact. So it's a type of fluorescence. It's electrofluorescence, if you will. So anyway, since this time, there's been a long history of far ultraviolet observations of the Earth from low Earth orbit, which I won't get into very much, except with one exception. But for a couple of decades now, people had the idea that maybe we could do something very similar to that lunar observation by flying a spectrograph to look at the Earth in the far ultraviolet and put it at geostationary orbit. And there's lots of traffic to geostationary orbit. There's of course the NOAA observatories, but there's also a huge amount of commercial traffic because of the communication satellite industry. It would be nice if NASA put their own satellite at geostationary orbit, but people had the idea that maybe NASA should get more into the hosted payloads way of deploying instruments, basically taking advantage of satellites that are already going to geostationary. So they started, this was in various strategic plans and roadmaps and surveys, the idea that we might want to do this, but it was not, it was kind of, it was kind of a small community of people that were really interested, and of course a lot of people wanted to compete for the opportunity to do it. The instrument that was selected is called GOLD, Global Scale Observations of the Limit Disk. It's an ultraviolet imaging spectrograph, measures temperature, composition, electron content at night, as I mentioned, and it does it from geostationary orbit. It's run by Richard Eastis, principal investigator. He's at the University of Central Florida. The instrument is actually being built at LASP right here in Boulder. Bill McClintock is the instrument PI, the deputy PI of the mission, and the instrument PI. And the project scientist is Alan Burns here at HAO. He's at the AMS meeting in New Orleans this week giving a talk about gold, of course. And so we conceived of this thing this particular mission was born in 2005, 11 years ago. Richard and Alan and I had dinner at also in New Orleans at the AGU spring meeting. It's just a few months before Hurricane Katrina, and decided we should go after this opportunity, which was being sort of floated by NASA in conjunction with the RBSP mission of all things. And I suggested to Richard that he think about having LASP build it, and he got in touch with Bill McClintock, and the rest is history. Very long history. When you've been competing for something like this for over a decade, I can't. Well, in preparing this talk, I ran into some old slides that made me want to reminisce. The final hurdle was actually now 3 years ago. Just tells you how long these things take. When we went to headquarters for the second time, after many, we were selected, then descoped, and selected, then descoped. Finally, we got our big chance, made our second pilgrimage to headquarters to pitch it to John Grunsfeld. And this is one of the slides from that presentation. You have to have a benefits to society slide here, and I'm glad to see so many folks coming by from NOAA series and I'm glad to have been recently working with some of the folks from NOAA series, because I think that there's terrific near real-time opportunities to use these data. And we had the advantage of working with Alan Stern on this, because he had an appointment at the Central Florida at the time, and And he's got his own ideas about how to pitch things at headquarters, but he's on his way to the Kuiper Belt, so you can't argue with success. So we were working on this Science and Society slide. He said, well, you got to have some people on it. It's the benefits of society slide. It's got to have people on it. And I was like, oh gosh, okay. So, I mean, we have the picture of the sun. You have to have the word heliophysics in there somewhere. There's a true statement on this slide. This is what we really, really want to do. And it's hard to make that into, canonical science goals. But everybody in this room knows, this is what we really want to do. We want to use these data to make our models better. Not that they're not pretty good. And of course, we think that there are going to be operational benefits to having this kind of real-time, near real-time monitor in space. And so Alan says, well, I had some picture like of cosmic or something. And Alan said, well, you want to talk about GPS, you got to have a person with a GPS. And so Mark Langton found this stock image on the web and said, let's use this. Girl lost in the mountains. There's an ionospheric storm going on. There's no cell phone. The cell phones are out. The GPS is given the wrong answer. And so it's a stock image that was copyrighted. And I said, oh, not only you're telling me I'm going to show this picture to John Grunsfeld at NASA headquarters, and it's going to cost me $11 to do it. But I downloaded the image of Tracker Babe here, and went off to headquarters. Oh, and this one, I sent off one of my early Airglow simulations, which you can see over here, to Andre Kirinos at Florida. And he put this thing together, and he sent it back. Oh God, more stock art, nice photoshopping job though. And he said, no. I put your image on my computer screen, and I showed it to my kids, and they were really excited about it. And they were asking questions and pointing. So I took a picture of it with my phone and sent it back to you. And so my only thought about that is, well, first of all, Tracker Babe, if you're out there, thank you. And I can only hope that some of my colleagues will be as excited about these Airglow simulations as Andre's kids.
You need to add a thought bubble that says damn substorm.
Yeah, exactly. Well, you can see she's thinking, what's going on? She doesn't know what's going on, but something's going on in the ionosphere, and it's throwing off the GPS. So here are our real scientific objectives. We want to understand, this is the most important one. We want to understand how geomagnetic storms change the upper atmosphere. We want to understand solar response to solar variability, solar photon variability. And then we want to measure the effects of waves and tides propagating from the atmosphere underneath. And then at night, as I mentioned, we see the ionosphere, and we will be able to measure the irregularities. The instabilities are sometimes called bubbles that form after dark in these equatorial regions, and that also could be very important, basically as an operational demonstrator, I think. To put this in a more colloquial vein, it's always seemed to me and many that getting this big picture view of the Earth's upper atmosphere is going to be beneficial intuitively, just as it is for weather observations. Think how much it's done for hurricane tracking. This is actually Hurricane Sandy. Low Earth observations can do a lot for us, but it gives us a funny view of the world. It's one where we're locked in solar time. We're progressing slowly in solar time. It's what the meteorologists call an asynoptic view. And so we would really like to see everything all the time. But I think Aaron Ridley calls it MEAT, right? Measure everything all the time. Or maybe he calls it meal ticket. But gold is just one instrument. We wish we had three of them. Maybe if this turns out to be a valid proof of concept, we will have three of them someday. Because then you could measure all around the Earth as the sun rises and sets. Remember, geostationary It's actually in orbit. It's just locked with a particular point. So the sun does rise and set, as you will see. So you can't really see anything all the time. So the view you get of the Earth is in some ways as complicated as the low Earth orbit asynoptic view. And that is one of the main lessons of these simulations. Now, if you could see everything all the time, you would see perhaps the E region of the ionosphere, where the aurora is predominant, the neutral temperature, the composition, and the F region electron density. These are the main things we're going to measure from gold. And I know some of you have seen this simulation before, but I'll run it one more time just to make a point, which is that as these big auroral storms break out, you get an enormous temperature perturbation that's all through the atmosphere, all through the upper atmosphere. It's global in extent, not just in the polar regions. And as I loop it through, notice this band of composition change that propagates from the pole to the equator. Here come one more loop. Here comes the storm. Here's the temperature effect, and there's that band of composition change that comes very highly structured. Now, this is in the model. This is what the model thinks is going on. Here is the low Earth orbit view of it from a publication. This is by Crowley et al. Using observations from the Time spacecraft, the global ultraviolet imager, GUVI. Makes very similar observation, but from low Earth orbit. And here's the measurement of a similar storm. Now, with GUVI, in this asynoptic view, time runs backwards. That is to say, from right to left. There's no law that says time has to run from left to right. If you think about it, as the Earth rotates, if you have to stack your orbital swaths this way, or if you put continents underneath, they'll look inside out. So they decided to keep the continents looking like continents, and time runs this way. And as the storm starts here, you get this wedge of composition change. This is atomic oxygen to molecular nitrogen changing as a function of latitude and time. The model, this is the actual measurement, this is the model simulation, captures it pretty well. The model seems to overestimate this recovery, or whatever it is that's going on as this wedge recedes. I think what this is that band we can see in the so-called synoptic view when we watch the whole thing spread towards the equator and come back. And it'll be really interesting, especially because during the gold mission there will be another low Earth orbit mission called ICON to try to validate that hypothesis and see if what the model is representing really does have any relationship to reality. Yeah.
In that plot, the observation seems to show enhancement high latitude on the last day, but the model seems to show a very big completion.
Oh, yeah, up here. Well, no, I mean this is sampling the model as if it were GUVI. So it should be it should be reasonable. You make an excellent point.
There are some depletions early on, but
Yeah, I mean, it captures this feature, it captures this feature less so. But this is in the model does not seem to be does not seem to be realistic.
It's in the wrong hemisphere.
Yeah. Well, you know, this is November. This is that Thanksgiving storm. November 03. He's running it off of Hellas. So this is northern hemisphere winter, and it's I think we've seen that it's pretty typical of the model to underestimate the two. This is actually this is low atomic oxygen. the depletion of atomic oxygen following the storm in northern hemisphere winter. Well, these runs were done some years ago by a branch of the model which is not ours. So maybe we should try this storm again. We've been working on this storm, we've been working on this storm simply because this is a tough storm to integrate through, and it's been crashing the model. And just in the last couple of days, Ben has made some progress with help from a formulation that Art had used in WACM-X in increasing the stability of this run. So it's time to do this storm again. In fact, I should use it as the storm. The simulations I've been showing here, I'll show here, are from a different storm, but this one we should try this one now that we can integrate through it without crashing. So this is what the spectrograph looks like. It's two channels and they're identical. That's a benefit in terms of redundancy and operations and so forth. It increases the signal to noise when they're both doing the same thing. It also gives you additional flexibility that one channel can do its normal scanning thing while another channel is doing some sort of campaign observation. It produces disk and limb scans. On the day side, we get temperature and this O to N2 ratio, the so-called composition. Atomic to molecular composition is what it really is. Night side, there's electron, O plus density really. And then on the limb, we get stellar occultations when a star sets behind the limb, and from that we can infer molecular oxygen. It's based on designs that LASP has flown to other planets. Virtually every planet in the solar system has a spectrograph designed by Bill McClintock orbiting around it. And it will be deployed on a geostationary communication satellite. The ride is provided by a company called SES Government Services. It's one of the first services they're providing for the government, and kind of a pioneer in that sense. It'll fly on an Airbus satellite called SES-14. It deploys at 47.5 west. That's right over the mouth of the Amazon, just outside of the mouth of the Amazon River, which is not a bad place for us. It can just see Europe, see the Americas. It can see all those radar stations below. The launch is in late 2017. It's electric propulsion, so it takes about 4 months to get to orbit. And here are the basic specs. It's got a pretty decent data rate, and it's all real time. There's no onboard storage. There's no store and forward. There's hardly any. There's hardly any. I mean, there's standard instrument electronics, but there's very little receiving electronics. The satellite thinks it's a transponder. It's just generating bits, and it beams the bits to the ground as fast as it can. It's a TV station. So, yes, of course it has real-time capability. The inside of it looks sort of like this. I got some more detailed stuff on the optical path if people are interested. But it's basically F5 Wadsworth spectrograph with 3 different choices of slits and a scan mechanism to pull the slit back and forth across the Earth in order to generate that image cube. And the detector is an Ozzy-Sigmund delay line detector. It's a photon counting detector. It detects every photon event and gives the XY coordinates in the detector plane, and that is what is downlinked to the Earth. So it's kind of unique compared to the way you would more normally think of a space flight instrument with CCD and a predetermined array, and then some kind of accumulation time, and then some store and forward. It's not like that. You say, oh, there was a photon. Boom, there's the photon. It's a TV station. Also gives us a lot of flexibility in the way we bin up the data. So this is the observing idea. You have a slit that is oriented the north-south direction. It moves across the disk. It takes 15 minutes to make a scan. And then it goes back the other way and does the other hemisphere. So each channel is capable of doing the entire disk and limb in half an hour, just under half an hour. It has a little spare time in order to which to scan the limb, catch a stellar occultation if necessary. But there's 2 channels, And so one channel will be doing one hemisphere while the other channel is doing the other hemisphere. So our advertised cadence is a half an hour, but in fact there's 15-minute capability if you're using both channels. Say again? Well, it'll be calibrated in the lab, of course. There is an onboard flat field source especially for measuring detector degradation and to assess the burnout. You know, you get these bright lines tend to burn out ruts in the microchannel plate. But the absolute onboard calibration will be done primarily with ultraviolet stars. We're tracking them all the time anyway because we're doing these occultations. Well, we don't track them. What we do is we park, the occultation slit is very broad, so it gets a lot of photons. We park the occultation slit on the limb and watch the star set through it. Or if you think of it in an inertial sense, as we rotate, the satellite scans the star down through the atmosphere. So the temperature is measured by the rotational shape of these Lyman-Burge-Hopfield bands, which are generated by molecular nitrogen. That's all these bands here. They get broader if it's hotter, narrower if it's cooler. We fit that with the band model and infer the temperature. The composition is measured by the ratio of this atomic oxygen emission to those same bands. The temperature on the limb, when the slit's off of here, is determined by the scale height, by the slope of the emission profile. We'll use primarily LBH to do that because the atomic oxygen also has an ionospheric component that you see at high altitude. And at nighttime, that high altitude ionospheric component will be used to measure the ionosphere and hopefully see bubbles in the ionosphere. The O2 profile is done in absorption in the middle thermosphere by, as I mentioned, parking this broad slit on the limb and watching the star set through it. Any questions about this? There's a lot of information on this slide, but not a lot of detail. Yeah?
The temporization best is 15 minutes, but how do you want it bubble?
Well, the bubbles are thought to have a lifetime of minutes to hours. If you look at the ground-based images or the simulations, they develop fairly slowly. But one of the things, one of the mysteries is, when you see them from GUVI sees them all the time in low Earth orbit. But if you measure a bubble and then you come back 90 minutes later on the next orbit and you see another bubble, and well, is that the same bubble? Did it move? You have this asynoptic problem. When you see them from the ground, either through radio observations or through Airglow imaging, you can watch them move, but you have a limited field of view. You don't know, if you have several of them marching in succession. I think that the synoptic view is going to be really powerful for this. Once we get into twilight and there's less to do on the day, there are going to be these special modes where we take both channels and scan the equatorial region as quickly as possible in order to get as many photons as we can to measure the ionosphere. And we can move that scan mirror as fast or slow as, it's completely programmable.
The main thing determining your temperature resolution is how many photons you can get.
Yes, it's noise limited, and in fact, we're really right now. Everybody's very happy because the detector came in better than spec, and so a lot of these concerns about photon counting are reduced. But the big challenge for this mission is getting enough photons. That's one of the reasons we have two channels. The statistical issues are especially salient at night, of course, because the ionosphere emissions are much, much dimmer. And so, and of course, at solar minimum, everything is lower. Tim?
You can be controlling the horizontal scan.
Oh, yes.
Can you stop the scans and you just stare at one slide?
Yes. Yes, the whole thing is programmable, and as I said, the way you build up your maps is infinitely flexible because you're not, there's no inherent resolution other than that slit width. We have our nominal plan, but then of course the nominal plan is always subject to change when you get on orbit, and then there'll be special campaign modes. One idea that's been floated already is park the slit and look for waves at that location because you get much better sensitivity, if you're just staring at one spot. So it'd be sort of like this. You just put the slit here and see if you can see waves moving through it. And then for the nighttime modes, you could park the slit and just watch for bubbles along that slit. But we really would like to get the global morphology of these things. And so we may have to wait for the solar activity to pick up a bit to get really good bubble measurements, but I'm pretty optimistic. I mean, we would like more spectral resolution. We might like more signal to noise, but I think it'll be pretty good. If we were designing a bubbles instrument per se, without all these other goals, it would probably not look like this. It would probably be a photometer. And in fact, back in 2006 or so, talking through with Dave Rush, who's saying, well, what we need is a spectrographic channel and a photometric channel, but the cost of the thing goes through the roof once you start putting a whole lot of bells and whistles on it. But the real way to see at night, all this goes away except for 1356 and 1304, which is off spectrum down there. And so you don't need spectral resolution. What you need is sensitivity. So a photometric approach, such as was used by Image to look at these phenomena, would be superior. But again, I think part of the value of this is a Pathfinder mission. We want to prove that you can make valuable observations from geostationary orbit, and so we're trying to do a lot of things, and hopefully demonstrate the value of making these equatorial irregularities. They go by many names: scintillation, irregularity. Mike Kelly coined the term convective ionospheric storms. Trying to come up with something to describe what we're talking about when we see these enormous fluctuations of the equatorial ionosphere. Michael. No. Well, they're not. I mean, we have our field of regard, and there's no possibility of the satellite maneuvering for us. They maintain nadir pointing very consistently with very good accuracy and precision, and they maintain it. They want it to be there. I mean, they have their commercial customers. They want a full-time operation. One of the main operational constraints for us is solar avoidance. When the sun is anywhere near the Earth, we don't like to. They're planning on turning the instrument off when the sun is in the field of regard. So we won't get measurements in the middle of the night. The bubble measurement will be primarily a post-sunset measurement, which is the time when you see the most bubbles. That's the most interesting to look at. But we will not be making measurements all night. And as I said, if you really wanted to design this as a nighttime ionosphere instrument, you would have to do things a little differently. You would have to have very big baffles. I'm baffled by how the visible geostationary imagers that take the cloud maps that we're familiar with do sun avoidance. There must be times where they just can't look at the Earth. Infrared, I think, is a little easier. The ultraviolet, you just don't want to point ultraviolet instruments at the sun, as you all know.
Solar avoidance a problem at solstice too? When you're
Less so.
you can't, you still can't observe a type.
Well, you get 22 degrees for Solstice, right? So 22 degrees is still a little close, but but of course it narrows the cone. Nominal operational plan is we turn off at 2100 local. You know, perhaps with some on-orbit experience, the operators could be persuaded to be a little play it a little closer to the edge, especially if there's something worth seeing. For the day-glow observations, you're pretty much on. You've pretty much lost your day-glow capability once you get past 2100, and I'll show that in a sec. So this is what I've been working on. It's a observation system simulator, or sometimes called an OSSI. You have to have this if you want to be able to make sense of your measurements. In principle, you would like to have this long before you even conceive of your instrument, in order to be able to guide the design. Usually, you do this sort of thing after launch. We've tried to learn from experience, and I'm trying to work ahead. The idea is that you have a modular system where each of these arrows is actually a file-based transfer. And that facilitates multi-institution approaches, and it facilitates swapping components in and out. So the idea is you might have a theoretical model, you might have an empirical model, or different flavors of them, and you feed the output from that, your basic fields, temperature, density, composition, ionosphere, into an Airglow model. This is my Airglow model. It's called GLOW. There could be another component here, such as Auric. Naturally, the one I'm working with is the one I've got, which is GLOW. GLOW produces a global map in 3 dimensions and time of the emission function, but it does not produce what you will see. In order to do that, you have to make line of sight and radiative transfer calculations. Before that, this piece here could belong up here, but it happens to be here. This stands for Lyman-Burge-Hopfield vibrational rotational bands. This is the band model. This stands for line of sight radiative transfer. We do it on the disk and limb. It goes into an instrument simulator, and hopefully that goes ultimately into analysis algorithms so we can guide the development. The reason this is down here is that just structurally, this is the way I'm building it. This is all Fortran. This is all IDL. Just sticking with what I know. This stuff here is parallel and very fast. This I am working on parallelizing GLOW. It's a easy parallelization problem. Every point on the globe in 2 dimensions is independent. And for this stuff here, this stuff is pretty time consuming, but I'm looking to find ways to parallelize that as well. There's this thing called IDL Bridge, which a few people around here know about, and I'm going to try to learn how to use it. It's basically a way of doing multiple jobs in IDL. I think that since all the analysis is also going to be built in IDL, it's going to be beneficial to learn how to use some of these multi-processing techniques, because there's going to be a lot of data coming out of this thing. So I just wanted to walk through how this structurally works. The idea is you could have any one of several models, both theoretical and empirical. I've got these interfaces to the TiGCM and TimeGCM. We're working on this. Valeria is doing some work on a Wacom-X interface. And then there's a WAM-C-TIPI interface that some of our colleagues from NOAA SWIPC series are working on. Thanks for coming. That stuff goes into, this is what those outputs might look like. Those go into the GLOW model. GLOW is a complicated sort of thing. I started to describe, if I really wanted to walk through exactly how these emissions are generated, I'd walk through all of these steps. Basically, either aurora or photoelectrons, which are excited by solar ionization, create a cloud of energetic electrons throughout the atmosphere. You put these into an electron transport algorithm, which looks a lot like a radiative transfer algorithm, except it happens at many, many, many different electron energies. That goes, those electrons bounce into neutrals, chemistry ensues, and emissions occur. Is that good enough for now? And anyway, that enables you to build up maps of what the airglow look like. That goes into this vibrational rotational band thing. The reason you have vibrational rotational bands is you have two electronic states of the N2 molecule. And so in each electronic state has many different vibrational levels. Each vibrational level has many different rotational levels. And so each of these vibrational transitions forms a band. Like say, let's say the 3-0 band, which is this one from here to here. And each band has a rotational structure, and the width of the band is determined by the temperature, because the hotter it is, the more the vibrational levels get populated. So you need to have a really good band model in order to be able to take the measurement and then look back at it and say, oh, this band was yay wide. That means the temperature must have been so-and-so. So this is one particular one. I now have two, so we can do some comparisons. These things are these are computationally intensive. What I did is I built up a lookup table for every temperature at every wavelength. I made a big file, because nowadays you can make big files, and so you just load that into storage, and now you have every wavelength at every temperature, and you can just instantly say what your rotational spectrum should be.
It purely depends on temperature. It doesn't depend on other inputs.
The intensity depends, of course, on the airglow. There are other things going on. The vibrational population, the vibrational distribution, is sensitive to a number of parameters. Doesn't vary that much, but it's a little controversial because you have collisional factors going on, and you have radiational factors going on. And but in order to be able to do this rotational temperature fitting, you have to match the vibration. You have to match the intensity of each band. And there's several ways to think about doing that. One way is to just go and match each band. Say this band is so bright, I'm going to make it that bright and fit the rotational width. Another way to do it is fit all the upper states. I color-coded these. The reds are all upper state 4. The oranges are all upper state 3. The greens are all upper state 2, and so forth. And I think I said that right. I can't quite see the screen from here. And so you could just, in principle, once you've got the upper state population, all the other bands should follow their Frank-Condon factors. But, we learn not to be principled. There's always surprises out there. So this is one of the main motivations beyond this. We need a really good simulation in order to develop these analysis algorithms. And then, of course, there'll be surprises once we get to orbit. But this is the biggest analysis challenge. I mentioned that signal to noise is the biggest observational challenge in this mission. Getting the temperature out of this type of observation is the biggest analysis challenge for this mission. And in fact, we are looking for help on in the algorithm development department. This gets fed into a line of sight ready to transfer code that I'm working on. That enables you to build up a map of the emission brightness you will observe from orbit on the disk and on the limb, and of course with spectral detail. And then that gets fed into an instrument model, which is noise, slit width, spectral broadening, distortion, pin cushioning, all that stuff. Most of it undesirable. And I'm not going to talk about that because Bill and his gang at LASP are working on that. Everything I'm going to show today is noise-free and assumes a 1 angstrom spectral resolution, which we do, of course, will not get. So what I'm going to do instead is I'm just going to walk through relatively, try to do this quickly, how this line of sight machine works. You know where the satellite is, and actually I built it so that the satellite could be at an arbitrary location. For geostationary, I haven't put the satellite into motion yet because geostationary enables you to keep that fixed. But so you know this vector, and then you set up a coordinate system of what the instrument sees. In this case, looking back at the Earth, and I define some coordinates in the east and north direction that I call chi and psi, similar to x and y, but they're angles. And then the angle that from where you are, from where your instrument is, to some point at the Earth, in this case, a simulated point, I'm calling that angle from the nadir vector to that point alpha. You can compute alpha from chi and psi. And then you now have a way of defining this observational vector. So you know this vector, you know alpha, you know this vector. And what you'd like to know is the position all along the atmospheric path at the Earth. If it goes through the atmosphere and then hits the solid Earth, I call that a disk measurement. We would like to know R1 and R2, and of course we can find R1 and R2 if we know how long V is. In the limb case, it looks like this. It pierces the atmosphere and then it leaves the atmosphere. It has some tangent point, and which tends to define the location of the limb observation. Again, if we know the length of V, we can calculate R1, R2, and RT. Now, V can be computed from a variant of the law of cosines. This is the flavor of law of cosines where you know an angle and a side, but the angle is not between the sides, it's next to the sides. And it's a funny version because it has a plus or minus and a square root in it. And that comes out of the trigonometry. You can look it up. It's not the law of cosines I learned in high school, but it's very valuable because with this law, if you know S and you know alpha, you can calculate V. But then, of course, you have this funny plus or minus and this determinant here. Well, it turns out that if it's an acute triangle, then you subtract the determinant. That's shorter than this. If it's a oblique triangle, then you add the determinant. The case where the determinant is zero, if all this is zero, then it's just V equals S cosine alpha. Well, that's familiar. That's this case. That's this tangent point case, where this is a right angle, and V equals S cosine alpha. That's simple. What if the determinant is negative? Well, then there's no solution. There is no V that intersects the Earth. That's the case where the line of sight misses the Earth entirely. So I sort these observations in chi and psi into their determinant categories to decide if it's a limb, disk, or non-observation, and build up a map of all the points in this simulated detector. What I then do is calculate, I calculate this path through the atmosphere, divide it up into segments. First I transform to Cartesian coordinates, right? Because once you're into Cartesian coordinates, it's easy. You have S, you have V, so you can calculate this thing here, divide it up into segments, add up all the little pieces of segment, and that gives me an integration of the emission function through the atmosphere, which is my column brightness. And I build up this observation cube. I do that at each of 300 wavelengths, so that I have a complete spectrum at all the different observation angles. So, and then I do that over and over again every half an hour through the day so that I can make an Airglow simulation. And this is what it looks like in 1356, the atomic oxygen emission. This is just a single day quiescent solar maximum equinox case. Now, good question. The case of LBH It's well less than 1, but there is absorption by O2. And in the case of 1356, some of these observations, the optical depth approaches 1, but it's fairly thin. I'll get to that in a moment, but I'm realizing that that I'm running out of time, and I'm going to have to skip over the radiative transfer stuff. I should say though that something I should have said before. The reason that far ultraviolet measurements are attractive for the upper atmosphere is simply that O2 is an absorber in the far ultraviolet, and basically below about 100 kilometers, it's a complete absorber. So it blocks out the lower atmosphere. You don't see the clouds. You don't see visible light coming from the upper atmosphere. So the beauty of O2 is it provides a black screen behind what you want to measure. But there's still O2 in the upper atmosphere, which gets in the way. It does some absorption. These emissions at these altitudes are weakly absorbed by O2. So here's the image cube simulation. You have a slit that we're going to pass along the disk. All along the slit, you image. And perpendicular to the slit, you disperse, of course. And along the slit, you image. So you get at every point, as you move the slit, you get this image square, or rectangle, which is in wavelength along this axis, and in space along this axis. And you can see here's some day glow for the splits here. Get some night glow. Remember I said at night, the LBH goes away, and all you can see is the 1356. And then up here, that's the aurora, where you see both. We'll see the aurora in these observations. It's going to be difficult to make sense of it because it's sort of on edge, but it's going to be something for guest investigators to try to figure out. So here's what it looks like as you pass the slit across the disk. All the emissions shoot up as you measure the day glow. Then as you go across the terminator, everything dies away except the aurora, and then it goes off the disk, and then you come back and do it in the other direction. And then finally at the end, you make your limb measurement. Limb being fairly bright compared to the disk. Here's that atomic oxygen emission for a different case, a December solstice, where the sun illumination is tilted. You see a pretty good ionosphere in these, though. Again, the LBH looks similar, but there's no nighttime emission at all, except for the aurora. Now, when you take their ratio, now you get an indication of that atomic oxygen to molecular nitrogen ratio. This is just a ratio of the emissions. There's no additional analysis going on in here. Now, this big orange thing, that's just night. The interesting part comes actually during the day, see, where you see at night. At night, there's no LBH, so the ratio becomes infinite. So my color scale isn't very good here. But during the day, you can see this is a solstice case, so you have a big gradient, a lot more atomic oxygen, a lot more atomic oxygen in the winter hemisphere. Let's try a storm. Here's the famous 2006 AGU storm. I'm going to try to run these both at once. You see them changing together. And you'll see the aurora get big during the storm, and then that day, you get this big wave of composition change. It's hard to see unless you look at the ratio. Let's do that. Remember, this is just night. And here's the quiescent day, night. Here's daytime again. Now here comes the storm. There's that band of oxygen spreading down to the equator, which changes the density of the upper atmosphere. It's not just composition. Because the upper atmosphere is mostly oxygen, when you get this big bloom of oxygen, the whole density of the upper atmosphere goes up and the satellite drag goes up. So I've used up my time. What I really want to do is talk about radiative transfer, because that's what I've been doing the last few weeks. But what I think I should do is let me see if there's anything else that I wanted to talk about before I stop. But sorry, I'm just looking at the other slides. Yeah, I have a bunch of stuff on these radiative transfer details that is interesting but specialized. Oh, I'm inadvertently hopping ahead to show you all my radiative transfer slides. But what I'm going to do is I'm going to stop here because it's an hour seminar, and anybody that wants to talk about radiative transfer can stay for a little while, but not too long, because there's a few people that came by because they thought maybe they could meet with me after the seminar's over. So, but in answer to your earlier question, Michael, yes, there's a lot of radiative transfer going on, and it has to be taken into account in a suitably sophisticated analysis algorithm. So that's what I've been doing a little lately. And other than that, I'm just going to stop here and see if anybody else has any questions. Thanks.
Two questions. First, what's the lifetime of the mission?
It's a nominal 2-year mission. Nowadays, most NASA missions are nominal 2 years, after which you have to start applying for extended missions and so forth. And that's a reasonable thing, because you know, if it gives them a chance to see if you're actually working or not. ComSats have a typical lifetime of 15 years, and these last spectrometers have been orbiting planets for decades, right? Well, typical lifetime of one of these instruments is 10 years. So we are hopeful of an entire solar cycle of data, but NASA has to agree, and I think that's part of the challenge is showing the value of these measurements in a timely way. And let me hit this drum one more time. There is some history of NASA satellites that proved of operational value, having lives after their lives by finding other ways of supporting their meal ticket.
Second question. In terms of the lower atmosphere forcing, do you have a sense, can you sort of decouple the...
Oh, it's going to be much harder than we think. Well, you know, we did these simulations to show the effective tides and how you can detect the tides and so forth. We see in the model you can turn the tides on and off and see what the difference is, but you can't make the atmosphere do that. I got talking about the mission in general and didn't have time to go. Like I said, if you want to look at more of these, you can stick around. I'll show you, run some of these by you in more detail. But let's just go back to this original one, right? It's nice and big. As you come through the terminator, you see how much as you approach the terminator, you see all of these gradients. There's a reasonable one there. You can see all these gradients in the image that have nothing to do with the atmosphere. It's just you have limb brightening towards the limb. It's brighter towards noon than towards the terminator. You have all of these geometric effects from your observation geometry and your sun illumination geometry, and so the tides, being heavily solar influenced, are heavily convolved with this observational function. Non-migrating tides, or anything that's any kind of planetary wave, anything that's different, that's not solar locked, will be a little easier to find. But it's going to be a difficult analysis problem to pull this systematic stuff out. By the same token, you know, again, it's going to be like the last solar minimum. We're going to launch into solar minimum, and things are going to be quiet, and there's going to be nice, many days on end that are very, very similar from a space weather perspective, where we would like to be able to pull out some of these lower atmospheric effects. But to zeroth order, this is an aspect of the mission that's discovery oriented. You know, our question is, can we see tides? You know, this is like these missions are coming from like 160 kilometers. Are there significant effects from tides at those? Let alone, can we analyze them? Can we see them at all? So I don't want to oversell that aspect of the mission, but it certainly is part of what we're after, and it certainly is going to provide for very fruitful analysis challenges for people that want to get involved. Tim?
The contrast of the day side and the night side when you've got terminated down the river, does that put any challenges on the detector? Do you think you'll be able to see the less bright region without contamination?
Yes, well, especially at equinox, you know, the whole slit moves, and you're getting the bright scattered light out of your slit. But I mean, you know, this is a question for Bill. But I do know that mitigating these scattered light effects is a very large preoccupation of the instrument design, and I have every reason to believe that it's going to be done successfully. I'm pretty sure that there aren't any problems with the detector saying getting swamped or saturating. The biggest problem with saturation is actually those stars. When you put that big occultation slit and park it on the limb, and that star comes through, those things are bright. That actually caps our data rate. But one of the things we've done here, and one of the things that I'm working on but not going to talk about, is we've excluded 1304 and Lyman alpha from this observation. Unlike that one I showed from the moon. Those things are really bright, and those will swamp a delay line detector. But they're very hard to analyze. They're optically thick, they're confusing. So we want to make sure that scattered light from Lyman alpha and scattered light from 1304 don't get into the detector. And keeping that bright stuff out of there, we think we can get a very clean measurement of 1356 and LBH.
So I have a question in terms of sort of Primeval temperature at this junction. So we are interested in assimilating this data, especially in the form of emission rather than feed. And then the benefit of doing it is probably some sort of error goes into the Primeval process. And then what I'd like to understand is how nonlinear that sort of extraction of temperature information out of rotational shape of empty. It seems very complex.
It is very complex. And temperature will be a much more difficult assimilation target than composition. I mean, we've talked about this. We should start with the composition. People have done composition before. This temperature measurement has never been done before, not in this way. I mean, people have made LBH temperature measurements, but not from geostationary orbit. I remembered why I wanted to jump ahead and show my conclusion slide, because it has words on here that some of the people in the audience will like to see. The real challenge with the temperature is this. Well, first, the first challenge, of course, is getting a reasonable temperature out of those bands. You know, fitting the band model and getting the rotational vibrational distribution right and getting a temperature. But what does that temperature mean? It's an effective temperature. It's the temperature all through your line of sight, weighted by the emission intensity, after having taken O2 absorption into account, right? So it doesn't come from one spot on the atmosphere. In the atmosphere, it comes from a variety of altitudes, and the temperature gradient in that region of the atmosphere, around 160 kilometers, is pretty steep. So so what are you going to do with this effective temperature? Well, its variability is going to tell you something, right? It should vary in a systematic way, and its day-to-day variability should tell you something. But in terms of, and of course you can, and in fact, that's one of the goals of this work. I've done this. I've said, okay, now I've made this observation, and here's the spectrum that goes with it, and here is the effective temperature the model used to generate that, right? Because I can integrate along my line of sight, weight it by the contribution function, so that it's weighted according to where the photons are coming from, and take that average and say, that's the effective temperature I think I'm measuring, according to the model.
Is it unique temperature? Can you come up with
Is it unique?
different temperature profiles?
Yes,
different emission
of course.
So it's not
Well, we got this Bates-Walker theory that says that the thermosphere gets hotter as you go higher. And of course, a variety of slopes could fit that. But we really don't think, maybe in the aurora, but we don't think you're going to see some kind of funky oscillating temperature profile. If that were the case, you would not be able to measure it with gold. Trying to figure out how to use this effective temperature effectively is a challenge even beyond obtaining that effective temperature. I should also say, of course, that we have ways of validating this. I mean, I have this wonderful plot of our, the satellites like to make these plots of ground station conjunctions. So I have this plot of a ground station conjunction with Arecibo. And it goes, it's 1 for 18 hours a day, right? For 18 hours a day, we are over Arecibo. Well, actually, we're always over Arecibo. We don't observe all the time. So anytime Arecibo takes a ion temperature measurement profile, we will be looking down at it. And so we have something to compare to. And I should say that below 200 kilometers, it's assumed that the ion temperature and the neutral temperature are roughly the same. So they can measure what we think we're seeing, and we can use that as a validation approach.
useful on the limb.
Oh, yes. Well, again, a goal, the mission goal and the back pocket challenge. Our resolution, we're far away, and so our spatial resolution on the limb is not large. So we're not claiming that we're going to be able to get all sorts of high resolution limb stuff and composition and temperature. All we're going to try to do on the limb is get that topside scale height, from which we can get an exospheric temperature, which is not the same thing as its effective temperature from the middle thermosphere, but will be very valuable in understanding, these two measurements together should be very valuable. And I claim that really GUVI gets an exospheric temperature, because once you scan down into that soup, you're integrating along this long path. Don't get me started. And so on the limb, we're going to try to fit that topside profile and get an exospheric temperature. But we will get full spectra all through the limb, all the way down. And team members, guest investigators, dilettantes with spare time on their hands can try to figure out how to get temperature, composition, all sorts of interesting stuff out of it. 1493, we think 1493, the atomic nitrogen emission line, it's a big irritant because it gets in the way of the bands and nobody knows what to do with it. But it's probably a really valuable measurement if only somebody can figure out what to do with it. I mean, there's a whole thesis in 1493 for somebody.
So you're assuming that Arecibo is still running?
Hickamarca. I meant Hickamarca. I said Hickamarca, didn't I?
That's not my question.
It's a good question. You're asking good questions, though.
All your, I don't understand the terms for that.
It's a lot like the chromosphere.
Could it be disturbed, say, by a very big volcanic eruption? Your whole pre-calibrated maps of how all of this responds and so on.
Only in a dynamical way. I mean, the volcanic ash can't make it that high. However, it's
Ash is not the only thing that can blown off by a volcano.
if there were significant perturbations to stratospheric gases that changed that were able to actually penetrate to the turbopause and change the chemistry, that would be really interesting. It wouldn't change our calibrations or anything. But the possible effects from something like that come first to my mind would harken back to Nick's question, which is if you have changes in stratospheric dynamics that were driven by volcanic events or other events, strat warms and auroral, solar proton events. There's any number of things that can change stratospheric dynamics, and the linkages with which those dynamics can propagate upward into the thermosphere, changing the wave budget, changing the turbulence budget, changing mixing parameters, changing gravity, changing planetary waves. Those could be very interesting, challenging for this type of measurement. Again, from a single satellite. If we had 3 of these, so you could measure the whole temperature, you could get the full 24-hour tidal map, it would be more powerful. But it's not gonna screw up our calibrations or anything. Just offer interesting opportunities for analysis.
Quick question. So, can some of the modeling study you did here, is it practical to apply those for data simulation, or is it just too expensive?
Oh no, that's one of the reasons we're doing this, is to build a machine that's available that people can use to do things like data assimilation. With data assimilation, there's different schools of thought. The more reduced the quantity you assimilate, the more errors propagate into your model. The more primitive the quantities you assimilate, the more difficult and time-consuming it is, right? Ideally, you would be assimilating the raw spectra directly into the giant whole atmosphere model of some flavor. That's not feasible, but we would like to be able to assimilate, these brightness ratios, of which are indicative of O to N2, or the temperature, these effective temperatures. But because there's these observational geometric effects, if you just say, oh, this is O to N2, and we've taken out all that geometry for you, trust us, that's one way to approach it. But as you've seen, as you get to the terminator, and if you're just looking down at the nadir all the time at noon, it's a pretty easy problem. O to N2 is very proportional to those emission ratios. But as you start looking at all these different angles, and the sun's shining down at all these different angles, that answer changes. So I think that utilizing these simulations in order to create the kernels that will be useful for doing the assimilation into the model will be valuable. But that work is in its infancy. But there's several people who are very interested in it, and I was pleased to see so many of them showed up.
All right. Thank Stan again for a great talk.